Today I'm going to talk about section 5.3, which talks about the area of a triangle. And so where do we get the area of a triangle anyway? It actually came from the area of a rectangle. So let's actually talk about that a little bit. So here I have a rectangle. The area of a rectangle is equal to the base times the height. So down here's my base, and this is my height. And so up here is also the base. This is also my height. And so again, we're gonna find the area of a triangle by using the area of a rectangle. And so how are we gonna get a triangle from here? We could actually create two right triangles by slicing this in half. So here's my right triangle, here's another right triangle. And so we've just created two right triangles out of this rectangle. And the area of these two triangles is 1/2 base times height, because we just cut the area of a triangle, the area of a rectangle in half. And so the area of a triangle, of a right triangle specifically, is equal to 1/2 base times height. So again, notice that we've created two right triangles, base and height. Okay, and the area is equal to 1/2 base times height. So it's the half of the area of the rectangle. So we're gonna, again, we can only use that if we have a right triangle. But we've been working with a lot of oblique triangles in this chapter, and so we're gonna have to use a little bit of different formulas to actually find the area of the triangle that we're working with. So let's look at this theorem, the area of a triangle. The area of a triangle is given by any of these three formulas. Okay? And again, it depends on what you have. That's going to determine which formula you're going to use. So if you're working with B, C, and alpha, then you're going to use the first one. If you're working with little a, little c, and beta, you're going to use the second one. And if you're working with A, B, and gamma, then you're going to use the third one. But let's talk about how we ended up coming up with these three formulas. And so here I have it looks a little bit like it's a 90-degree triangle, but this is just an this is just an obtuse triangle here. And so let's try to find the area of this triangle here. So let's suppose that we're given alpha, we're given little b, and we're given little c. Okay, so I'm going to try to prove the first formula that we have here. A is equal to 1/2 b times c sine of alpha. And so we're going to have some alpha. We're given b and c. All right. And so the area right here is going to be 1/2 base times height. But again, we don't have the height right now. But we can drop a perpendicular line. And we know that that's going to give us the height of the triangle. All right. Well, what is b? Well, we know b is b. If it's given, then it's b. And we're trying to figure out what h is. We're given alpha and c. So how are we going to find h? Well, we know that we can write h in terms of alpha and c if we take sine of alpha, opposite over hypotenuse. And so if we do sine of alpha is equal to h over c, and I solve for h, then I get that h is equal to c times sine of alpha. And so I plug that into my original formula. A is equal to 1/2 b, and my h is c times sine of alpha. And notice that that's actually the first equation of the theorem. So we just proved it. All right, so again, you don't have to memorize them as long as you know how to derive them. All right, so let's actually get our hands dirty a little bit and try some of these examples. So find the area of the triangle with the given parts. Round to the nearest tenth. All right, so let's create a couple of triangles here. All right, and we're given alpha, we're given B, and we're given A. So we have a little alpha is equal to 39.5 degrees. We don't have gamma and we don't have beta. We do have little b, and so this is going to be little b is equal to 12.6. And we are given little a, which is going to be opposite, the length opposite of my angle alpha. And so little a is equal to 13.7. All right. So the only thing here is that we cannot use any of the formulas for the area of the triangle. Not yet, at least. Because again, in order for us to actually use one of those formulas, we need to have the two sides and its included angle. And so in order for us to use one of those formulas, either we have to find little c or we have to find alpha. And so again, that's just your personal preference. And I think that I'm gonna find gamma. I have a couple of options. I can use the law of cosines, and that's going to help me find gamma. Or I could find beta by using the law of sines, and then once I know alpha and beta, then I can find gamma. I think I'm going to do that. I think I'm going to find beta and then find gamma. Because again, I like using the law of sines. I think it's a little bit easier to use. And so we have that sine of beta over little b, which is 12.6, is equal to sine of alpha, which is 39.5, all over little a, which is 13.7. I'm going to solve for sine of beta. And so we have sine of beta is equal to 12.6 sine of 39.5 degrees all over 13.7. Again, I multiplied both sides by 12.6. So if I plug this into my little calculator, I get that sine of beta is 0.585. And when I take the inverse to find beta, I get that beta is equal to 35.8 degrees. And so now we can use the property that all the angles inside a triangle sum up to 180. And so we have that alpha plus beta plus gamma is equal to 180 degrees, which is going to give us that gamma is 104.7 degrees. All right, awesome. We know all our angles actually. So all we have to do is find the area. So now we have little a, we have little b, and the included angle gamma. So let's actually use the theorem for the area of a triangle. And we have the area is equal to 1/2 little b times little a. Again, the order doesn't matter. Multiplication is commutative. So 1/2 little a or little b times little a times sine of gamma. So let's plug all this in. So we have 1/2 13.7 times 12.6 times sine of 104.7 degrees. And if we plug that into our calculator, we get that the area is equal to 83.4. So again, there's different ways of approaching this problem. So you could have used the law of cosines to find gamma and not even have to worry about finding beta. But I like using the law of sines, so I use the law of sines first to find beta. And then once we know beta and alpha, then we can find gamma. So again, it's personal preference. Let's try another example. This is example 2. So find the area of the triangle without using a calculator. All right, so that means that we're going to have to use some of the special triangles perhaps. So we're given 30 degrees. We're given that the longest side is 8 feet and one of the other sides is 4 feet. You can label your triangle however you want. So if you want, we could have this be alpha, and again, it doesn't matter if you don't like alpha, maybe we use beta. Okay, so maybe that's beta this time. And so the length opposite of beta is going to be little b, which we don't know. Okay, and I'm just going to let this be alpha. And so the length opposite of alpha is going to be little a. So this is going to be little a. And this missing angle here is going to be called gamma. And the length opposite of gamma is going to be my little c. Okay. So notice that this example is a little bit more simple because we actually are already given an angle that is an included angle. So we already have A, we have C, and we have beta. And so we don't have to do any extra work here, which is nice. A little break. So my formula that I'm going to use is A is equal to 1/2 little a times little c times sine of beta. Because again, we already know A, we already know C, and we already know beta. And so if we plug everything in, we get 1/2 times 4 times 8 times sine of 30 degrees. So notice that it said without using a calculator because we know what sine of 30 degrees is. And so A is equal to 16 times 1/2, which is sine of 30 degrees is 1/2. And so the area of this triangle is just 8 feet squared. Okay, because again, it was in feet, so feet times feet, feet squared. So that is the area of this little triangle here. Example 3. Find the area of the region to the nearest whole number of square units. All right, so here we have this region. Right, we're given some things about this region. Okay, like these two sides are both 3 feet. The base is 5.7 feet. And so we're trying to find the area of this. Okay, well, there's a couple of things that we can do. We can break it up into different little pieces. So I could already see that we could break this up into three different pieces. Okay, 2 of them are triangles, and 1 of them is a square or a rectangle. I think I'm gonna do it that way, just because I like breaking it into smaller pieces. So I'm going to break it up into 3 different parts. And so I'm going to drop a perpendicular line right here. So again, it's a little hard sometimes. So again, I'm going to drop a perpendicular line, which is going to create a 90-degree angle here. I'm going to drop another perpendicular line here. It looks simple, but it's not. And there we go. Oh, it looks a little crooked, so I'm just going to move it a little bit. So I think that might work out. Okay, it looks a little terrible, but okay. Yeah, it definitely looks terrible. So there we go. And let's move this one a little bit also. Okay. All right, I'm playing over here with my shapes. All right. And so we know that the base is 5.7. Okay, we know that we have a couple of um of angles here that are given and some of the sides. So what I'm going to do is I'm going to find the area of this right triangle. Okay, notice that both of these triangles are exactly the same. All right, so I'm going to find the area of that triangle, which is going to be the same as the other triangle, and then I'm going to find the area of the rectangle, and I'm just going to sum up all the areas. I think it just makes it easier if we just break it up into little pieces. And so I'm going to start off by doing finding the area of the right triangle. And so I'm going to write down here, I'm going to call this area of right triangle. All right, and so here we go. I have this right triangle. It's 90 degrees. So notice that if this is 90 degrees and this is 60, then that means that this has to be 30. And this length here is 3. And so let's use a little bit of our trig to find the other side. So let's find the height here. And I'm going to call this base 1. So B sub 1. We could use sine or cosine to find either h or b sub 1. So base 1, I guess. And so I'm going to actually find h first. And so we're going to be using sine of 60 degrees is equal to h over 3. And so if we solve for h, we get h is equal to 3 sine of 60 degrees. And we know that sine of 60 degrees is the square root of 3 over 2. And if we plug this into our calculator, we get that this is approximately 2.598. So it's not the nicest number. So I'll just leave it with all of those numbers after the decimal. All right, now I'm going to find B1, or the base of 1. So I'm going to use cosine here, and so I have cosine of 60 degrees is equal to B1 over 3. And so I have B1 is equal to 3 cosine of 60 degrees. And cosine of 60 degrees is 1/2. So B1 is equal to 3 over 2. And if we plug that into our calculator, actually we don't have to do that. because 3 over 2 is just 1.5. Okay, so we have found the length of base B1. Right, so actually that's going to help us find a couple of different things, because if the length of the little triangles is 1.5, then we can actually find the base of this rectangle here. And so this is good. We've made a couple of progress here. Well, we made some progress. So let me redraw this here. We have, I'm going to draw it a little bit apart. And again, of course, it's not drawn to scale, right? But we do know that this is 3. We know that h, the height, is a really ugly number. 2.598, and the base is 1.5 feet. And so this is going to be also 1.5 feet. And remember that the whole length of the base was 5.7, and so we can just do 5.7 minus 3, and that's going to give us the length of this rectangle, the base of this rectangle. So the base of my rectangle is going to be 2.7. So we know the height of the rectangle, we also know the base, so we could easily find the area of this rectangle. And we could also find the area of these triangles. Okay, so we're still working on the area of the triangles. I got sidetracked a little bit. And so let's actually figure this out. So again, this is 60 degrees. And so we could use any of the formulas. Since we're working with right triangles, we could actually just do area is equal 1/2 base times height. We don't actually have to go back and use the formulas for the area of any triangle. And so that made our life a little bit simple here as well. So we have the area of my triangles is going to be determined by the area is equal to 1/2 base times height. And again, if you don't want to, if you want to practice using the other formulas, then you could totally do that. That's fine. And so here we have area is equal to 1/2. My base is 1.5. My height is 2.598. And so my area here, and I'm going to round to the nearest whole number, is 2. So the area of both of my triangles here is 2. Okay. And now I'm going to find the area of my rectangle. Which is the area is equal to base times height. So we have the area is equal to, the base is 2.7 times 2.598. And so the area of my rectangle is going to be 7. So all we have to do now is sum up all the areas, and that's going to be the area of this region that we're talking about. And so the area of the region is 2 plus 2, because remember we had two right triangles, plus 7, which is the area of my rectangle, and that it gives us 11 feet squared, because remember we're working with feet. Feet is our units. Last thing I want to talk about is Heron's formula. And Heron's formula says that the area of a triangle with sides A, B, and C is given by this formula. And so if we're given a triangle with just the sides, with no angles at all, then we cannot use our previous method. But if we have all the sides, we can use Heron's formula. And so S here is A plus B plus C in the numerator and 2 in the denominator. So let's actually use this formula on example 4. And so here we're given that the sides are 5, 7, and 8. Let's first make sure that let's actually make sure that these sides here actually create a triangle. And so let's just recall the triangle inequality. We have to make sure that the sum of two sides has to be greater than the third side. So let's just check. So let's check. So we have 5 plus 7, which is equal to 12, and that's greater than 8. Awesome, that's good. But again, we have to check all the sides. So 5 plus 8 is equal to 13, which is greater than 7, which is the third side. Check, that's great. And last one is going to be 7 plus 8, which is 15, and that's greater than 5. Check. Okay, so we are working with an appropriate triangle. This is an actual triangle that we can have. And so now all we have to do is find the area of this and round to the nearest tenth. All right, so we need to find S first. So S is equal to A plus B plus C all over 2. And so here we go. We have, and again, it doesn't matter which one A, B, and C are. So I'm just going to sum them up. I'm just going to do 5 plus 7 plus 8 all over 2, which is going to actually give me just 10. So now all we have to do is plug everything into this Heron's formula. And I would encourage you guys to look at the proof of that. It's really interesting. So now the area here is equal to the square root of S, which is 10, times 10 minus A, and I believe I said that A was 5, and then 10 minus B, which I believe I put 7, and that doesn't actually matter, the order, and then 10 minus C, which is going to be 8. All right, and so now we just plug all of this in our calculator, or again, we could try to simplify this a little bit. So this is going to equal to the square root of 10 times 5 times 3 times 2. And so if you take the square root of, in this case, 300, we get that the area is equal to 17.3, rounded to the nearest tenth. And that is it for now. So thank you for sticking around.